Hello everyone. First of all, I wish to thank organizers for giving me a chance to present our recent work. And I am a PhD student working in the Department of Physics and Astrophysics in the University of Delhi. My research is basically centered around the testing fundamental cosmology using different cosmological observation and statistics. So today here in this talk, I will discuss a model independent test of variability of type 1a supernova luminosity. So this work is based on this archive number, and with the help of my collaborators, we published this work in JCAP this year. First, let me address the motivation of this talk content. So as we know, the first observational evidence for the cosmic acceleration appeared from type 1a supernova observation. And since the initial core mass conditions are about same in all cases, so therefore these supernova tend to have the same luminosity, or we can say that same absolute magnitude and light curve, which is shown here in this figure. So that means for all kind of type 1a supernova are formed just after the Chandrasekhar mass limit. So therefore we are saying that all kind of type 1 supernova should have the same luminosity or same absolute magnitude. And so therefore the basic assumption behind the type 1a supernova analysis is that the intrinsic luminosity of a supernova is independent to the redshift. But however, in the recent years, the many dedicated studies have concluded that the light curve fitting analysis of these type 1a supernova depends on their host galaxy masses, metallicity, and local star formation rate. Since these terms, for example, the metallicity evolved over time as per the literature survey, so therefore there may be possibility that the luminosity of type 1a supernova may change with time. So therefore, in this work, we relax the standard assumption that which was type 1a supernova have the intrinsic luminosity independent to the redshift, and we investigate the variation of the absolute magnitude with redshift. So to understand this analysis, so first let me build the basics of type 1a, basics of cosmology, and then I will talk about the observations and statistics used in this analysis, and finally we will discuss the results and conclusions. As we know, in science, any theory depends on some fundamental assumption or principle. Similarly, the cosmology is also based on some underlying belief or principle of simplicity. So this principle of simplicity is called the cosmological principle, which states that on the largest scale, the universe is to be uniform, or we can say it states that at the large enough scale, the universe is spatially homogeneous and isotropic, or we can say that on the large scale, let's say scale of greater than few hundred MPC, the universe is uniform. So this assumption, the assumption of large scale homogeneity and isotropy appears to be an accurate description of our today's universe. So under this assumption, the Friedman, Levantre, Robertson, Walker give a metric for an expanding universe, which is given by this one. And as you know, this matrix is known as the FLRW matrix, and this FLRW matrix defines the geometry of the universe, where 8 is the scale factor. C, here we are considering C as a unity, and 80 is the scale factor of dimension length, which describe how the distances in a homogeneous and isotropic universe expand or contract with time. So now to relate the geometry of a universe to its mass energy content, Einstein gave equations which are known as the Einstein's field equation. So in the Einstein field equation, the first two terms of the left hand side we can see tells about the curvature of the space-time and can be calculated using the Riemannian tensor, and lambda is the cosmological constant, and right hand side of this equation represents the energy momentum tensor. So basically this Einstein field equation tell us how the space-time behave in the presence of energy momentum tensor. To define, so here you can see the R mu are the Ricci tensor, Ricci scalar. To describe the matter part, we consider a perfect fluid, since the perfect fluid are isotropic in their rest frame, which satisfy the condition of the cosmological principle. And for a perfect fluid, this energy momentum stress tensor is given by this equation, and where P and rho are the pressure and density of a fluid in their rest frame. So basically, we discussed the main three ingredients of cosmology, which are the FLRW matrix, Einstein field equation, and energy momentum tensor. And using these quantities, the Friedman derives two equations, which are known as the Friedman's equation. So these two equations are given by this equation. So basically, the Friedman equation describes the evolution of the scale factor with time. So basically, here you can see A dot and A double dot. So A dot is the variation of the scale factor with time. If we combine these two Friedman equations, we can write a single equation, and which is given by this equation. So left hand side of this equation denotes the acceleration. The first term of the right hand side is the pressure and density term, or we can say the gravity term. So which are the gravity term, and which is always P and rho are always the positive for matter and radiation, and this negative sign denotes that the gravity slow down the expansion. The motive of the introduction of the lambda freedom term was that in order to justify the Einstein's idea of a static universe, so there should be a term on the right hand side which can compensate this gravity term. So therefore, the Einstein introduced a term to explain the static universe, which is given by this equation. So using a Friedman equation, we can easily define the Hubble parameter. And Hubble parameter is the ratio of the scale factor time variation in the scale factor to the scale factor. So I mean the H is given by A dot by A, and so basically this Hubble parameter describes the expansion rate of a universe. And here we can see that how the Hubble parameter varies with redshift in terms of different cosmological density parameter that we will discuss now. So the parameter redshift. The parameter Z is the redshift, and which this cosmological redshift we can easily calculate by just observing the spectrum for a given element. So where lambda naught is the observed wavelength and lambda is the emitted. And also this scale factor and the relation between the scale factor and the redshift is given by this formula. And different kind of cosmological density parameters that we already included in the formula of Hubble parameter. So first let me define the cosmological density parameter. So omega m is the matter density parameter. All are matter density parameters, which is given by this one. And similarly, the density parameter for a curvature in the cosmological constant is given by this one. So all these cosmological density parameters are the dimensionless quantity, and the sum of all these density parameters is equal to 1. So now let me introduce the different kind of the distances. And so the most basic and difficult measurement in the cosmology is the distance. So the basic assumption is that the all distances somehow measure the separation between events. So in a crowded and expanding universe, the measurement of distance is a tricky business, because in the expanding universe we can imagine that the separation between the two objects are continuously changing. So therefore, the distance measurements have played a key and surprising role in the dynamical universe. So in cosmology, there are many ways to specify the distances between 2 points. So first, let me define the co-moving distance. So co-moving distance, we can imagine that let's say we have 2 points which are moving with the Hubble flow, and their separation remains constant in all epochs. So therefore, this proper distance dp is the proper distance, and we are dividing by the scale factor 80, and the proper distance is also changes with the same factor of 80, and therefore we can say that the co-moving does not evolve, does not change with the time. As we know that this co-moving distance we cannot measure directly, because we can measure the co-moving distance for a static universe, means we cannot, but as per the observations, the universe is not static, it's expanding. So therefore, to measure the distance from a distant star, we require some standard population of objects. So the standard population of object, I mean in our universe, we have some objects whose size are known, and we can define the angular diameter distance as shown here. On the other hand, we have some objects whose luminosity are known and constant throughout the space-time, and we can use them as a standard candle. So here we can see the variation of the angular diameter distance and the luminosity distance with the common distance and redshift. And if we club all these three kind of distances, we can write down, we can define a common formula for all these parameters, all these distances. And here we can see that all these distances depends on the different combination of the cosmological parameters. Till now we build the basics of the cosmology, that all these formula we will require in the throughout the whole analysis. So now let me introduce the standard candle, which is type 1a supernova. So a type 1a supernova occurs when a white dwarf star acquires an additional mass from a companion star when it reaches a critical mass 1.4 times the mass of sun. The latent pressure in the center of the star sparks a runaway nuclear reaction, and the white dwarf explodes. We assume that we know the intrinsic or absolute luminosity of L for a given source. For a given source, which is called the standard candle, that radiates isotropically, and this is the assumption, one of the assumptions. And type 1a supernova are believed to be approximate a standard candle, and they are used to map the cosmological distance that we will discuss. And let us assume that we observed a flux F from a standard candle with absolute luminosity L at a distance say dl. So we had dl is the luminosity distance, and we can define this luminosity distance in terms of the apparent or absolute magnitude as given by this formula. In the log scale, we can define a relation between the absolute magnitude or apparent magnitude with luminosity distance, and further using the cosmic distance duality relation, which is a relationship between the luminosity distance and angular diameter distance, and we can define the apparent magnitude in terms of the angular diameter distance as we can. So here we can see that we can define a apparent magnitude or distance modulus in terms of the angular diameter distance, absolute magnitude. And as we already discussed, this angular diameter distance depends on one cosmological parameter, that is omega k naught. So here in this formula we have two free parameters, that is omega k naught and nv. So these two parameters, our aim is to estimate these two parameters. For this one, we use two observational data sets. So in the first observational data set, we are using the Hubble parameter measurement using the cosmic chronometers. So this is the cosmic chronometers. So this database has 31 data points from redshift 0 to 2, and here the 31 data points are shown. And for the luminosity distance, we are using the recent and largest data set of 1048 data points. And this data and this supernova data set is up to redshift 2.26. So here is a typo. So it should be 2.26. Sorry. So for the redshift matching, of both these datasets, since Hubble parameter dataset and Pantheon dataset have the different redshift, so to use these two both dataset in a single analysis, we need a redshift matching. So for this one, we apply a Gaussian process on the measurement of Hubble parameter, and we reconstructed the Hubble parameter using the Gaussian process. And using this reconstructed Hubble parameter, we estimate the angular diameter distance that we required for the distance modulus equation. So similarly, for the parameter estimate, we use the we just define the chi-square in terms of the distance observed distance modulus, that is MB observes, and theoretical reconstruction of MB, which depends on the MB and omega k. And in this analysis, we use for the Pantheon dataset, we consider the both error, systematic and statistical error in our analysis. So our aim is to put the constraint on MB and omega k naught, and further our aim, as I explained, our aim was to check the variation of MB with respect to redshift. So therefore we consider the four different parameterization of MB. In the first parameterization, we consider the MB as a constant. For the flat and non-flat universe, we put the constraint on the we constrain on the distance absolute magnitude of a type 1a supernova. So roughly which comes out equal to minus 19.4. And also we can see that in the non-flat universe, the best fit value of omega k suggests an open universe, but at 1 sigma confidence level or 68 confidence level, this analysis support a flat universe. So further, to study the distribution of these parameters, we have shown the corner plots between these two parameters. So basically, these corner plots tells about the correlation between MB and omega k naught. So here we can easily conclude from this corner plot that there is no such correlation between omega k naught and MB, since this contour looks like a circle. So in the next parameterization, we consider a Taylor series kind of expansion for the absolute magnitude, that is MB. And again, by considering the flat universe or non-flat universe, we put constraint on these parameters. So similarly, we also shown the different kind of different kind of correlation between the parameters. And in the third parameterization, we consider some convergence series for the MB, and similarly in the both flat and non-flat universe, we consider we find the best fit value of MB and omega k, and similarly omega k we also find as the best fit value of omega k suggests in flat universe at 95 confidence level. And the correlation between all these parameters is shown on the right hand side. And in the last parameterization, we consider a logarithmic, and finally we get the result same as. So all these four parameterization gives the almost same conclusion. So the conclusion of this analysis is that in the flat and non-flat universe, all parameterization support there is no evolution of MB with respect to the redshift within at 2 sigma confidence level. And also the best fit value of omega k suggests a flat universe at 2 sigma confidence level. However, in the parameterization P2, P3, P4, the best fit value of omega k shows a mild preference for a non-flat universe, and 1D contour for all parameterization shows a negative correlation between all these parameters. Thank you for your attention.